You know, it is incredibly easy to take the morning routine entirely for granted. You wake up, you turn on the faucet to brush your teeth, you check your phone for the fastest route to work.
Right, you just hop in the car and go.
Exactly. You drive down a paved street, maybe you pass a garbage truck along the way. It all just feels like, life happening.
Just the normal daily chaos.
Yeah. But beneath all of that, beneath the water rushing through the pipes, the data hitting your phone, and the cars moving on the asphalt, there is a hidden, almost invisible mathematical web governing every single movement.
A very strict web, actually.
And today we are going on a deep dive to decode that web. We've gathered the core principles of transport network analysis to show you how our messy physical world gets translated into digital data that algorithms can actually use.
It's fascinating how it all works behind the scenes.
It really is. So, for you listening right now, whether you are trying to beat rush hour traffic or just wondering why the local fire station was built exactly where it is, we are going to expose the hidden logic behind your world. Okay. Let's unpack this. Because to understand how modern software routes our daily lives, we first have to understand what a network actually is.
It really is a matrix that we live inside without even realizing it. Because, well, in the context of spatial analysis, a transport network is not just some generic web of connections.
Right.
It is specifically a graph in geographic space that describes an infrastructure. And the crucial mechanism here is that this infrastructure does two things simultaneously. It permits movement and it constrains movement.
Meaning it dictates exactly where flow can happen and just as importantly where it cannot.
Exactly. We are talking about road networks, yes, but also railways, air routes, pipelines, aqueducts, and power lines.
So it makes me think of the human circulatory system. Like you have this massive network of veins and arteries.
Yeah, that's a good analogy.
But it's not just a map of where the physical veins are located in the body. It's about the strict physical rules governing how the blood, or in our case, the cars, the water, or the data, is allowed to flow through them.
Right.
If a vein is blocked, or if there's a valve that only lets blood flow in one direction, that changes the entire system.
It does, but with one major difference that makes this math so complex. Your veins don't dynamically change their capacity at 5 p.m. on a Friday.
Oh, true. Traffic is a whole different beast.
The city grid changes constantly. You are mapping the physical pipes, but you're also mapping the dynamic physics of the flow inside them. And if we connect this to the bigger picture, the foundation for our highly advanced dynamic GPS mapping systems actually starts with an 18th century brain teaser.
Oh, the 7 bridges of Königsberg. This is such a fascinating piece of history.
It really is. Back in the 1700s, the city of Königsberg was situated on a river. It had 2 large islands connected to each other and to the mainland by exactly 7 bridges. And the popular puzzle among the citizens was this. Could a person walk through the city and cross every single bridge exactly once?
And people literally spent years trying to walk this path, just wandering the city, trying to find the perfect route.
They did, until 1736 when the mathematician Leonhard Euler proved it was completely impossible. But to prove it, he had to invent a new way of looking at the world.
Right.
He realized the exact physical shape of the land masses, the geography, was just a distraction. It didn't matter if the island was round or square. All that mattered were the connection points and the paths between them.
He stripped away the physical map.
Exactly. He drew dots for the land and lines for the bridges, and by doing that, he essentially birthed graph theory.
He stripped away the physical world to find the underlying math. But looking at the timeline of this field, it took a really long time for computers to actually catch up to Euler's 1736 revelation.
Oh, a very long time.
Because in the 1970s, the early developers of geographic information systems, or GIS, tried to reestablish this connection to analyze transport networks, but they hit a massive wall.
They did. The early developers were trying to feed physical maps into machines, but early works, like those by Tinkler in 1977, had to focus mainly on simple schematic networks. They were incredibly basic.
Because they just didn't have the computational power. Early computers simply couldn't hold the massive volumes of linear data required to map a real city.
No, the memory just wasn't there.
And the algorithms were just too mathematically heavy for the machines of the 1970s. It wasn't until the 1990s that full GIS software implementations became a reality. It makes you realize how heavy the math really is.
It is staggering, which naturally raises the question of how a computer actually reads a physical map today.
Right.
Since early computers struggled with the sheer volume of real-world variables, how do you mathematically translate a paved, three-dimensional street with potholes and a coffee shop on the corner into something an algorithm can process in a fraction of a second.
Right, because my phone's GPS doesn't see the coffee shop or the trees. It has to simplify it. Does the computer just view a map like a giant connect-the-dots puzzle?
That is the core of it, yeah.
Mm-hmm.
The entire network dataset is built on two primary things, edges and nodes. Edges are simply the lines that represent the actual paths of travel.
Okay.
They can be precise geographic routes, tracing the exact curve of a highway, or they can be straight schematic lines, vector polylines, essentially.
So the edges are the lines connecting the dots.
Yes, and the dots themselves are the nodes. Nodes provide the network topology.
Topology.
Yeah, they represent the connection points, the intersections. Without nodes, the computer wouldn't know that two intersecting lines actually connect.
Oh, I see. Like an overpass crossing a highway on a visual map.
Exactly. Without a node placed exactly at that intersection, the algorithm knows you can't magically drop your car off the overpass onto the highway below. Nodes enable the mathematical model to calculate transport from one edge to another.
But the lines and dots alone don't tell you how to drive. If I'm looking at a blank web of lines, I don't know if a line is a dirt road or a 10-lane superhighway.
Right. A line is just a line.
And this is where the engineers attribute 4 distinct properties to these edges and nodes to model actual movement. First, there's capacity.
Yes.
This is basically the physical limit on the volume of flow, like the number of lanes on a highway, the diameter of a water pipe, or the bandwidth of a fiber optic cable.
The absolute physical maximum. Then you have the second property, which is impedance. This is a measurement of any resistance to flow or speed.
Like a speed limit.
Exactly. A speed limit is an impedance applied to an edge. A forbidden turn direction, like a no U-turn sign, is an impedance applied to a specific node.
Okay, capacity and impedance make total sense. But then we get to the third property, cost. And I have to admit, when I first started looking into how these algorithms function, the term cost threw me. Wait, so cost isn't necessarily money?
No, not at all. In network analysis, cost is not about money. It is the accumulated penalty of traveling along an edge or through a node.
Like a penalty in a game?
Yeah, it's based on the principle of the friction of distance. Most commonly, cost is simply measured in elapsed time.
So making a left turn at a busy intersection has a much higher mathematical cost than making a right turn.
Yes.
Even though it doesn't cost me extra dollars because it takes more time waiting for oncoming traffic to clear.
Precisely. The node representing that intersection has a mathematical cost assigned specifically to a leftward flow. And what makes modern spatial analysis so powerful is that these costs are dynamic.
Because of traffic.
Right. The cost of traveling down a specific urban street changes drastically depending on the daily rhythms of rush hour versus midnight.
Which brings us to the fourth property, flow volume. This is the measurement of the actual real-world movement taking place on the network.
Yeah, the literal cars on the road.
And this can be tracked in real time using sensor networks like those rubber traffic counters you sometimes drive over, or through general historical trends over time like the annual average daily traffic.
When you combine all four, capacity, impedance, cost, and flow volume, you transform a static image of a map into a living, breathing mathematical matrix.
It's amazing.
And once you have that matrix, the system has to actually do something with it.
Here's where it gets really interesting, because having a perfectly mathematically modeled map is completely useless unless you can actually navigate it. We are talking about optimal routing.
The most common task in a network is finding the optimal route connecting 2 points. And optimal is strictly defined as minimizing some form of that cost we just talked about.
Right.
That can mean minimizing distance, minimizing energy expenditure, or most often, minimizing time.
This is the absolute backbone of web street mapping applications. When you pull up your phone to find the fastest way home, it's running these calculations. And the most popular method for solving this point-to-point routing is called Dijkstra's algorithm. But how does it actually find the path? It can't just guess every single road.
Think of Dijkstra's algorithm like pouring water onto a physical maze. The water naturally flows down every possible path from point A simultaneously.
Okay, I can picture that.
As it moves, it keeps a running tally of the cost to reach every single intersection. High traffic or a slow speed limit acts like high ground, slowing the water down.
Oh, wow.
The exact moment a trickle of that water touches your destination, point B, the computer freezes the simulation. That specific frozen stream, the path of least resistance, is your optimal route.
That is a brilliant way to visualize it. It just searches outward in all directions until it hits the target.
Exactly.
But point A to point B is easy enough to grasp. What if you, our listener right now, are running 5 different errands all over town today? You need to hit the grocery store, the pharmacy, the post office, the dry cleaner, and the hardware store. Suddenly, a simple point A to point B water flow isn't enough.
No, it's not.
Yeah.
That introduces what spatial analysts call composite routing problems.
Yeah.
The scenario you just described is known as the traveling salesman problem.
Right.
It asks for the optimal order and route to reach a number of specific destinations. And mathematically speaking, it is famously an NP-hard problem.
Let's break down MP hard because that sounds intimidating. It basically means it is notoriously difficult for computers to solve perfectly because the number of possible route combinations explodes exponentially as you add more stops.
Exponentially is putting it lightly.
Yeah, if you have 5 errands, there are 120 possible orders you could do them in. But if you have 50 errands, the number of combinations is larger than the number of atoms in the observable universe.
It is a combinatorial explosion.
Uh-huh.
Now, if you are doing this on a blank map, it's nearly impossible to solve perfectly. But in a constrained network space, the physical roads actually limit the number of possible solutions.
Because you can't just fly over buildings.
Right, making it slightly more manageable for the computer to approximate the best path. And a broader generalization of this is the vehicle routing problem. This is what large delivery companies use.
Like an Amazon truck.
Exactly. It allows for multiple simultaneous routes to reach all the destinations, optimizing an entire fleet of vehicles at once to hit hundreds of stops.
So the traveling salesman is like a delivery driver with total freedom of order, just trying to hit specific houses in the most efficient way. But there is another type of problem called route inspection, or the Chinese postman problem.
Yes.
This one asks for the optimal path that must traverse every single edge in the entire network. My mind immediately went to municipal services. That's not a delivery driver, that's a garbage truck.
That's a highly accurate analogy.
A garbage truck doesn't just go to specific houses, it is forced to drive down every single paved street in a neighborhood.
And here's where the math gets highly counterintuitive.
Yeah.
You would intuitively assume that mapping a route for a garbage truck that has to touch every single street in a sprawling city would be much harder than mapping a route for a delivery driver who only has to hit 50 specific stops.
Yeah, covering the whole city sounds way harder.
But the reality is that the route inspection problem, the garbage truck, is actually a much simpler problem for a computer to solve.
That blows my mind. Why is driving everywhere easier to calculate than driving to a few specific places?
It comes down to the nature of constraints. We mentioned the Amazon driver problem is NP-hard because total freedom creates infinite variables. The computer has to calculate millions of jumping orders between disconnected dots.
Right.
But the garbage truck problem can be solved with what are called polynomial time algorithms, which essentially means the math scales reasonably as you add more streets. Because the truck must travel every inch of asphalt, the constraints eliminate the bad choices.
Oh.
You aren't guessing the order of random points. You are simply finding the most continuous, unbroken thread through a strictly defined web. Freedom creates computational chaos. Constraints collapse the variables into a solvable puzzle.
That is wild. The sheer lack of options actually makes the computation easier. So what does this all mean for the physical cities we live in? We've built this massive mathematical matrix that can thread a garbage truck through an entire city grid.
Yes.
But that exact same math has a reverse application. If it can track a moving object perfectly, it can also calculate where to permanently pour the concrete for the truck's garage.
You're talking about location analysis.
Yes, playing SimCity in real life.
It really is. Location analysis aims to find the optimal location for one or more facilities along the network.
Sure.
And again, optimal means minimizing the aggregate travel cost to or from a set of points.
Right.
So if you're a major retailer, you use this to determine exactly where to place a distribution warehouse to minimize shipping times to your retail outlets. Or you use it to figure out where to build a new retail outlet to minimize the travel time from the residential neighborhoods of your potential customers.
And there is a really fascinating distinction here between a blank, unmapped grid and a road network. If you are just placing a warehouse on blank map, finding the absolute center point among your customers is another one of those NP-hard problems.
Because again, too much freedom.
Exactly. You have infinite freedom, so you have to use heuristics. Heuristics are basically educated guessing algorithms like Lloyd's algorithm, which drop a pin, test the travel times, and inch the pin around until it looks optimal. It's a game of hot and cold. But because our real world is constrained by roads, the problem can actually be solved deterministically.
It removes the guesswork entirely.
Mm.
Because the roads limit the options, the computer can calculate the absolute mathematical best street corner to build on. And this location analysis is heavily tied to the concept of service areas.
Service areas, okay.
A network service area is basically an invisible buffer zone. It defines the exact area that can be reached from a facility within a specified accumulated cost, like a 5-minute drive time.
A great example of this is a fire station. If you look at a traditional paper map, you might just draw a perfect physical circle around a fire station to show a 2-mile service area. But that's not how the real world works. A fire truck can't drive in a straight line through buildings or across a river without a bridge.
Right. So a true network service area isn't a circle at all. It is an irregular, spidery shape made up of the specific street segments the fire truck can reach within a strict time constraint.
Factoring in all the nodes and edges?
Yeah, factoring in the impedance and cost of every single node and edge along the way.
And if you have multiple fire stations in a city, the algorithm assigns every single street edge to the nearest facility based on travel time. This produces a result analogous to a Voronoi diagram, where the whole city is mathematically carved up into irregular interlocking cells,
ensuring no overlap and maximum efficiency.
So if you've ever wondered why there are 3 coffee shops within a mile of your house but 0 hardware stores, this is the exact math deciding that. You are sitting inside one of those invisible algorithmic service areas right now.
We all are.
But what about the networks we literally cannot see? We talked about roadmaps and delivery drivers, but at the very beginning you mentioned buried pipelines and aqueducts. How do these network tools apply to something buried underground where we can't physically see the nodes and edges?
That is where fault analysis becomes crucial. This is a common application in public utility networks. If a water main breaks or a telecom cable snaps underground, you can't just fly a helicopter over and look for the traffic jam.
Right, it's just dirt.
It is impossible to directly observe. So the network analysis software takes reports that can be easily located, like individual customer complaints of water pressure dropping in specific houses, and uses the topology of the hidden network to deduce the exact location of the fault.
It traces the symptoms back through the invisible edges and nodes, calculating the flow of water backwards from the complaints until the lines intersect at the exact broken pipe. That's incredible.
This raises an important question, though, regarding the long-term sustainability of these massive systems. You can't just route traffic and fix broken pipes after they snap. You have to analyze the systemic health of the infrastructure over time.
Right, you have to prevent the breaks.
Exactly. Transport engineers utilize something called vertical analysis to ensure these networks survive their own complexity.
Vertical analysis, how does that differ from just finding the fastest route or placing a fire station?
Vertical analysis is heavily used in railway systems to ensure they remain as efficient as possible. It's an overarching complexity analysis that looks at day-to-day operating activities, problem prevention, control activities, and how the entire system's activities are developed and coordinated.
Referencing the work of Bednar in 2022 from the text.
Yes, exactly. It's not just about getting a train from point A to point B today. It's about ensuring the physical and operational network can sustain that flow effectively into the future. It's looking at the daily rhythm of the entire graph to prevent it from collapsing.
It's the meta layer keeping the whole system functioning. So to recap the journey we've just been on, we started with some citizens in the 1700s trying to cross 7 bridges in Königsberg, which gave us the mathematical concept of the node and the edge.
Right.
We traced how computers finally caught up, translating physical asphalt into a digital matrix of capacities and impedances. We explored how those routing algorithms, like water flowing through a maze, dictate the path of your delivery drivers and your garbage trucks.
It's all connected.
And we've seen how this exact same math carves up your city into invisible Voronoi diagrams to tell a fire truck exactly which roads to take.
What's fascinating here is how utterly reliant modern society has become on this invisible mathematical layer. It quietly translates physical, concrete constraints into optimal, flowing efficiency, shaping the daily lives of everyone listening without them ever noticing the algorithms at work.
It really is a hidden matrix, but I want to leave you, the listener, with one final thought to mull over. It's built entirely on one brief, almost throwaway detail in the research.
Okay.
When you look at the cutting edge of transport engineering today, modern traffic flow is now being studied using statistical physics methods. Think about that for a second. Transport engineers are literally treating cars, treating you and me like interacting particles in a giant physics equation.
Just particles bouncing around.
Right. As our mapped networks become entirely optimized by algorithms where computers know the perfect deterministic mathematical flow for every vehicle, will human drivers eventually be viewed by these systems as nothing more than unpredictable impedances and unnecessary costs? It makes you wonder how long the chaotic freedom of the human driver can possibly exist inside a perfectly calculated graph.